مرحبا، يعطيكم العافية. إن شاء الله اليوم التجربة رح تكون عن Solubilization of Mefenamic acid. As we explained before, a drug must be soluble before being absorbed in the media surrounding the receptors. Around 40% of drugs have solubility problems, so aqueous solubility is a key factor in designing different dosage forms. The solubility is defined as the maximum concentration or maximum quantity of the drug dissolved in a given volume of solvent at specific temperature. And here we work at 25 degrees Celsius. We will work for the drug called Mefenamic acid. It is a weakly acidic drug. It's a non-steroidal anti-inflammatory drug. Follow under this family of the drugs. Liquid dosage forms are important for patients that cannot swallow or for kids, so we must formulate it in a soluble or in a liquid dosage forms. Mefenamic acid has a low solubility in aqueous media but a high permeability, so it falls under the biopharmaceutical classification system in the second class. Knowing the factors affecting solubility is important to enhance solubility and choose the best solvent media for the drug. We will have different methods to solubilize weakly acidic drugs, and we will talk specifically about mefenamic acid. One of the methods is the pH modification. The second one is co-solvency, and the third one is salt formation. We weighed 0.1 milligram of mefenamic acid drug, and we will have different pHs with a buffer solution. The first three ones are the acetic acid and the acetate, sodium acetate, and the second one are the potassium buffer, hydrogen and dihydrogen phosphate. First of all, we will dissolve the mefenamic acid in a 50 ml of the pH 3, 4, 5, 6, and all different pHs we have. Then we will have shaking for 15 minutes to dissolve almost every ingredient or every particle in the mefenamic acid samples we have. Then we will filtrate them in order to get rid of any excipients to measure the absorbance of them. So we will measure 50 ml of the pH 3 and 4 and 5, and we will have 6, 7.4 and 8.2. Then we will fill them in a Erlenmeyer flask in order to prepare them for shaking. Then we will shake them for 15 minutes and then follow the filtration. This is the setup for the first part of the experiment. Okay guys, now we'll shake them for almost 15 minutes, and as we can see, the drug is not soluble in the aqueous media. It will stick on the walls and the upper surface of the liquid or the aqueous media. We will wait for 15 minutes in order to finish this shaking process, and if we notice any drug that is completely dissolved in this media, so we will add more mefenamic acid. If all drug is dissolved, we will add more solid particles. Then we will go to filter the mixture. In this process, during these 15 minutes, we will prepare a calibration solutions in order to construct a calibration curve. We will have a 0.002% weight per volume of mefenamic acid and sodium hydroxide as a stock solution, and then we'll prepare further solutions in order to find the absorptivity of mefenamic acid at specific lambda. Okay. During the shaking process, we have prepared the stock solution for mefenamic acid and sodium hydroxide, 0.1 molar sodium hydroxide. We prepared 0.002% weight per volume of mefenamic acid by weighing 0.002 gram of mefenamic acid and filling up to volume with sodium hydroxide. Then we will prepare further solutions in order to measure their absorbances, and as we already know, the calibration curve requires only to know the concentration, and the absorbance is already observed by the spectrophotometer. Then you can calculate the absorptivity of mefenamic acid, and the absorptivity won't differ as long as you're working on the same lambda, which is 287 nanometer. After filtering the mixtures, then we will measure the UV absorbance for every pH buffer at this lambda we said before. If we need or if we required any any dilution of any solution after filtration, we will dilute it as well with sodium hydroxide, 0.1 molar sodium hydroxide. Now we will prepare further solutions of this calibration curve. The stock solution is already prepared. We will withdraw from it a 5 ml in order to prepare 0.001 weight per volume of mefenamic acid in sodium hydroxide. This is now a graduated pipette. We put some of the stock solution inside a beaker in order to withdraw from it to prevent any contamination for the stock solution, as we will draw further times and many more times for another calibration curve solutions. So we will draw from it a 5 ml using a graduated pipette. We will fill it for 5 ml. And the last drop in the pipette won't be released as an uncertainty. We will complete filling the 10 ml solution with 0.1 molar sodium hydroxide, and we must be careful as the 10 ml volumetric flask is very fragile and small in size, so we need to take care of handling it. You fill it at the bottom of the meniscus of the line. Okay, we finished the second calibration solution. This is the first one, the stock one, and this is the second one. The third one we will draw from the stock solution 2.5 ml of the stock, and we will add NaOH 0.1 molar up to 10 ml. 2.5. This is a 0.005, and we need to label them in order to prevent any contamination or any mistaking. Okay. Up to 10 ml with sodium hydroxide. Okay. Now this is the bottom of the meniscus is reached, and the third solution is prepared. This is the fourth calibration solution. We will draw 0.5 ml of the stock solution and add it to up to 10 ml of sodium hydroxide. We will use different graduated pipette in order to reach the accurate volume, which is 0.5 ml. We will use a graduated pipette of 1 ml. It's very weak and very thin. I don't know. Okay. So 0.5. Okay, now we have prepared the fourth calibration solution, and all the calibration solutions are prepared in order to measure the UV absorbance for them and calculate the absorptivity from the calibration curve. We will use a blank of sodium hydroxide for these solutions in order to measure the absorbance of mefenamic acid, and we will wait for the 15 minutes shaking and then filtration of the mefenamic acid in different pH buffers in order to calculate their solubility in different buffers according to the pH difference. Now the 15 minutes is up, and as we can observe, the mefenamic acid is not completely soluble in these flasks, and it's more like another layer on the liquid media, as you can see. So now we will filtrate these solutions in order to get rid of excipients or any dissolved particle, as a UV spectrophotometer won't measure these solid particles, it's only measure the solutions. And now, as you can see, we have prepared the filtration setup of the solution. The first pH is 3, and we will filter the solution that has been shaken with mefenamic acid and the acetate and acetic acid buffer of pH equal 3. This is the twisted filter paper and the funnel. And any undissolved particle won't get down in the filtrate. This is the filtrate cake that won't be needed. After that, we will measure the absorbance of these solutions, of different pH solutions. If there is any absorbance above 1 or 1.5, we need to dilute it with sodium hydroxide, 0.1 molar sodium hydroxide. The blank of each of these buffers will be the pH, the buffer of each solution. As in the pH 3, the blank will be the solution, the buffer of pH 3 prepared first, and for like pH 4, it will be the pH 4 solution. So every blank will be different between the measuring the absorbance. It won't be the same blank in measuring the absorbance of each solution. If we dilute it with sodium hydroxide, we will mix the buffer and the sodium hydroxide as a blank in order to subtract the effect of sodium hydroxide or the buffer from measuring the absorbance of mefenamic acid in the solution. Now, as you can see, each solution is being filtered. We will take around almost 3-5 ml of each solution in order to measure the absorbance, and we will keep the buffer solution, these buffer solution pH 3, pH 4 that has been prepared first, in order to use them as blanks. If any dilution, as we said, is needed, we will use 0.1 molar sodium hydroxide, and the blank will be sodium hydroxide and the buffer solution, the specific pH. Now, as you can see, we have used the UV spectrophotometer at lambda equal to 87 nanometer. We will put a blank of sodium hydroxide in both double beam, so in both spaces here. We will put a cuvette of sodium hydroxide 0.1 molar, then we will auto zero on it. Firstly, we will measure the calibration curve absorbance of the calibration solutions. Okay. We remove any dust or any fingerprints from the transparent wall of the cuvettes. And then we will go for auto zero. Okay, we will remove the first cuvette. Okay, this is the first solution of the calibration solutions. This is the stock one with a concentration of 0.002% weight per volume. .943, and we can make sure that by this reading we will have all the calibration solutions will be below a 1 value of absorbance. You need to be careful about the 10 ml calibration solutions, as they are very small in size. So don't waste the solutions inside them. You have only like 2 trials, as these cuvettes capacity is 5 ml. Okay, a 0.493, and measure the absorbance of further solutions the same way by taking the absorbance values and then construct a calibration curve by plotting a concentration versus absorbance, and the concentration will be in the weight per volume. Weight per volume concentration unit, and then calculate the absorptivity by inserting the equation on the curve. Okay, now we will measure the absorbance of the solutions of mefenamic acid with different pH buffers. We will measure like 3 absorbances, and I won't measure every buffer I prepared before. I will start with pH 3, buffer of pH 3, and we will use it as a plank first, and then put the solution of mefenamic acid with the buffer to measure its absorbance after zeroing on the plank. Okay. Now this is buffer 3. The same lambda, 287 nanometer, and then will be auto zero. Okay, now we are ready to measure the absorbance of the mefenamic acid in different solution buffers. We will use different droppers for each solution to prevent any contamination. So every solution will have a special or different dropper from the other solutions. Okay, 0.11 absorbance for pH 3. I will measure the second absorbance of 7.4, pH of 7.4. Firstly, we need to remove the blank cuvette as well. And rinsing it with distilled water. And then add the solution of interest, which is the blank here. This is a pH of 7.4, blank buffer. You need to cover the lid between every measurement in order to prevent any burning of the lamps. Okay, so auto zero. Okay. As we said, different droppers for different solutions. As long as you are working below the measurement of 1.5 absorbance, you don't need any dilution. Okay, so here's like 1.13 is like acceptable values within the linear range, so no need for dilution here, but the main field will become with pH 8.2. We mainly will need any dilutions with sodium hydroxide here. We will test it first. Removal of any fingerprints or any dusts from the cuvette walls is done by chem wipes, as they are specialized in removing any small particles or dusts without leaving any fibers on the wall. So it's done mainly by chem wipes. This is the blank of 8.2. We will auto zero it. and then remove the cuvette, the below cuvette of the buffer, and then add the tested solution. Remember to cover the lid with the measurements. Okay, so you can see now we have an absorbance of 4, which is clearly outside the range of the Beer-Lambert's law that's used to calculate the absorbance and calculate the concentration. So you can't calculate the concentration using this absorbance value. In order to do so, you need to dilute these solutions, and we will use a 1 to 100 molar of, a 1 to 100 dilution of this solution with sodium hydroxide, 0.1 molar sodium hydroxide. Then you need to take into consideration that the blank used will be sodium hydroxide and the phosphate buffer of pH 8.2. After making the dilution, you measure the absorbance and make if it's after that becomes more than 1.5, further dilution is needed. This is the serial dilution, and you need to calculate or to use the dilution factor in order to measure the concentration and the solubility of this solution in the of these drugs inside the solutions you prepared. Now we will move to the second part of this experiment, which is studying the effect of co-solvent on drug solubility. The same drug will be used and the same amount, 0.1 gram of mefenamic acid. But here we will use a different method in order to measure the solubility and how it's affecting using different concentration of the co-solvent. It's well documented that co-solvency is a common way to used in pharmaceutical industry in order to enhance the aqueous solubility of the drugs. We will use here ethanol. We can use other solvents like propylene glycol, glycerine, polyethylene glycols, or abbreviated as BEGs. Here we will study the effect of ethanol, different concentrations on the solubility of mefenamic acid in aqueous solution. We will use a phosphate buffer of 7.4, the same one used before in the first part of this experiment, simulating the gastric, simulating the intestinal fluid, or sorry, the blood media and how the pH in our system. And we will use ethanol in different concentration. The same setup is prepared. Here we'll have 0 concentration or 0 volume of ethanol. Then we will move from 0 to 5, 10, 15, 20, and 25. And we will add the phosphate buffer in the prescribed table in your manual. We will add the 0.1 gram of mefenamic acid into each solution. And then we will move into shaker, the same shaker used before, in order to mix the mefenamic acid with these solutions to increase the interface with them. As you can see, mefenamic acid still insoluble and form like a second layer on the surface of the solution. In order to increase the interface, we will use the shaker here. As we said, the shaking will be used for 15 minutes. Then we will filter these solutions in order to get rid of any dissolved particle. Then we will use 1 ml of filtrate and dilute it up to 100 ml of sodium hydroxide, and then measuring the absorbance. Absorptivity is well known from the previous part. It's the calculated on your calibration curve. The same will be used from the previous part, and then you will plot a solubility versus ethanol concentration, taking into consideration the dilution we made after shaking and after using the filtrate. We use like 1 ml of the filtrate, filling up to 100 ml of the sodium hydroxide solution. Okay, and now we have started the shaking of these flasks. We will shake for almost 15 minutes. We won't prepare here any calibration solutions as we will use the absorptivity measured at the same lambda in the previous part of the solution. We will shake for 15 minutes, and then we will filter these solutions, taking 1 ml of the filtrate and filling or putting in the volume up to 100 ml of the sodium hydroxide. Okay, and now we have finished the shaking for these solutions. We will filter them using filter paper and the filtration setup you've seen before. And now, as you can see, the solution is not completely miscible. There are some particles, lots of particles are not dissolved. They are sticking on the wall. Now we need to filter them. This is an indication of how mefenamic acid is highly insoluble, and the dissolution rate is controlling its bioavailability. So we will filter it and measure the absorbance of this solution. But firstly, we need to withdraw 1 ml and filling it up to 100 ml of sodium hydroxide, the same concentration, 0.1 molar. Here's the filter cake. You can see some residues of the mefenamic acid on the filter papers. You don't need to wait for the whole amount to be filtered. You just need to take the amount as specified for you, like a 1 ml or a 50 or a 5. You wait for the amount needed. We need here for like 1 ml, so we don't need to filtrate it all or wait for filtering it the whole time. Okay, as I said, we will take 1 ml of these solutions. I will use the 0 concentration of ethanol using graduated pipette of 1 ml. Inside a volumetric flask, and up to 100 ml with sodium hydroxide. Washing the pipette or rinsing it with water, or use another pipette in order to withdraw different solutions of mefenamic acid with ethanol, different concentrations. Labeling here is very important. As you can see, if you missed labeling, you can easily messing up the solutions with the different concentration, so you don't know which label belongs to this concentration. Okay, here's like from 5. As I said, we don't need a calibration curve here. We'll use the same absorptivity value we calculated from the previous part in the pH method. The same will be applied as long as we working on the same lambda, which is 287 nanometer. Okay. This is a 0 concentration of ethanol, filled up to volume with sodium hydroxide, and now we are filling the second solution, which is 5% or 5 ml of ethanol in 45 ml of phosphate buffer with 0.1 gram of mefenamic acid. The blank. Okay, and now this is the absorbance of the 25 sample of mefenamic acid with phosphate and ethanol diluted with sodium hydroxide. We put blank of ethanol and phosphate buffer. We auto-zeroed on it on the same lambda we used before, and then we start testing the absorbance of different samples, different different ethanol and phosphate buffer concentration. Now this is the end of the practical part of this experiment. In order to further to know more about the calculation of the experiment, you need to watch again the theoretical part of this experiment and put your calculations and draw or plotting the absorbance versus concentration with dilution factor calculation in order to measure the absorbance of to measure the calculation or to calculate the concentration of different mefenamic acid in different solution buffers, and study the effect of co-solvent and the difference in pH buffers on the solubility of mefenamic acid and how it's enhanced or stayed the same.